Hi everyone, my name is Summer and today we will be discussing gravitational microlensing and its relevance to finding small black holes and determining if those black holes account for dark matter or not.
Okay, I'm going to start by talking about what gravitational lensing is generally, and then more particularly about microlensing. And the concept of gravitational lensing relies on Einstein's theory of general relativity, which means that massive objects can bend space, essentially. So gravitational lensing just means that massive objects in space can essentially act as a convex lens, just focusing light into a smaller area. Meaning that if a distant star is far away and then there's something in between, it can make it seem larger and brighter to us. So microlensing is using this concept of a massive object lensing light, but in a transient process and with smaller objects. So transient just meaning that in a reasonable amount of time, we can see the distant object get brighter and larger. And then when it does that, we know that something lends the light. So if we can see this transient process of it getting brighter and then dim again, and there's nothing detectable in between us and the object, then we assume that dark matter is the thing that lends the light. And dark matter is completely undetectable to us, does not interact with light, and does not emit any particles. But due to predictions like microlensing, we estimate that it makes up 25% of the universe, while normal matter is only 5%.
So now that we know what dark matter is, what microlensing is, we can dive into the theory of it, which started from Stephen Hawking and Bernard Carr, who claimed that a collection of these small black holes could be responsible for dark matter. Many scientists did not agree with this at the beginning, but this did pose a several decade-long question of, is dark matter just a bunch of smaller black holes? And so gravitational microlensing allowed us to find these small black holes due to the warping of the light surrounding the point image, or the image that you can see here is an example of that. And extreme accuracy is necessary for finding these really small objects, which could also be really dim. And NASA's Roman Space Telescope did provide that accuracy. So now we were able to find the mass, distance, and motion of these black holes through the galaxy, according to Ashley Balzar. And we were able to track these smaller black holes. So once we were able to start collecting this data, we were able to start analyzing it and discovering if indeed these small black holes did account for the dark matter that we see in our galaxy that we theorize.
And so a lot of different projects have basically tried and tackle this hypothesis and test it to see whether or not it is valid. And the one that I'm going to highlight today is the Subaru telescope project. So what this project aimed to do was observe gravitational microlensing effects within the Andromeda galaxy over a period of approximately 7 hours. And when this occurs, like we previously said, we should see an increase in brightness of a star for a period of time. And what the researchers anticipated were the microlensing effect should occur approximately 1,000 times over 7 hours to make up the bulk of dark matter. But after careful analysis, the data collected over this time span, the researchers were only able to identify one such instance. And with these results, this tells us that within the sample galaxy of Andromeda, black holes can only account for 0.1% of all dark matter present, therefore leaving us to conclude that black holes do not make up a substantial portion of dark matter within specifically this galaxy.
For the future of gravitational microlensing, essentially, as technology and accuracy improves, we're going to be able to do a lot more. One of the things that we're doing now that we're going to be able to do more accurately in the future is mapping our own galaxy using the background of the M31 or Andromeda galaxy. We'll also be able to better estimate ages of black holes discovered by LIGO, which is a very accurate microlensing telescope. And then as we build more telescopes, we'll be able to increase the fleet size, which will allow us to discover more data and miss out on a lot less of phenomena happening in the universe, and also be able to understand dark matter if it is black holes or if it's not in the universe's beginning. Beyond dark matter, we're beginning to apply microlensing to a lot of different topics, one of which is exoplanets. So as we search for exoplanets, It's a great way to search for life in the universe. You can also map nearby quasars, and we can also adjust and affirm advances in astrometry, which is essentially what we've been doing in class. And so we can more accurately, mathematically, and physically represent what's going on in the universe. And a last thing is understanding the importance of tidal tails and streams, which is pictured down below. So essentially, as galaxies move and expand in the universe, they leave behind a gaseous tail. And so using microlensing, we can understand better the importance of those.
And that was our project. Thank you for listening. And these are our sources.